Leetcode problem minimum moves to move a box is about pushing a box in a grid. We are given the description of a grid with some cells being walls, forbidden, and some are empty. Also there is some starting position of a player, a human that is in that grid, box, and the target location. Every move is pushing a box one cell to one of 4 directions, but a player must be next to a box. If player is on the right from a box, they can move it one cell to the left. We need to find the minimum number of pushes. It doesn't matter how much the human walks through a grid. If he is on the right from that box and wants to move all the way to the left of that box in order to push box to the right, they can do it, and we don't count those moves. Only pushes of the box count. If we could move the box however we like to 4 directions without a human, then this would be a standard BFS problem, where you need to find the shortest path from one cell to the other, and what you're given is a graph. This grid can be represented as a graph, and 2 neighboring cells or cells of that grid are vertices that are connected. Well, if both those cells are empty, allowed to move around. Then box can be moved to the neighboring cell, then to the neighboring cell, and so on till the target cell. But we have a human. This is additional twist in this problem. Let's analyze one of the given sample tests. Human is here, there's box, there's target location. Human can go up, then push box to the left by 1, this is first move, then again to the left by 1, this is second move. Then this drawing shows the current situation. Human can walk all the way to the bottom of a box and then push it up. This is the third move, so the answer in this case is 3. This is optimal number of moves. The answer would also be 3 if we could just move a box to a neighboring cell, as we can see in top left drawing. It's just 3, but human must do some extra walking and we don't count it. But it is important where a human is, and let's see an example. Here's a more complicated example. We are given this grid, every red cell is a wall, we cannot walk there. If we start here, and the box is just on the left from us, the only thing we can do first is push it to the left, even though box is just next to the target. It would be nice to just make one push, but it's impossible in that case. We can push box to the left, then unfortunately we need to keep pushing to the left. We could also go here below the box, but then we cannot push it up because there's a wall. Instead, we need to keep pushing left, then push left one more time. The situation will be box is here, we are here. Then we can move all the way here and start pushing it to the right. Eventually, box will be just below the target again, but we are here. We can go below the box and push it up. Instead of just one move, one push, the answer will be several. Here 1, 2, 3, 4, and back, I guess 8 plus the 9th move up. BFS and Dijkstra are algorithms that are able to find the shortest path in a graph, but this graph can have vertices that represent whatever we wish they represent. For example, in chess, we can say that the whole situation, the whole thing that happens on the board where every piece is one vertex of a graph. And we have some starting vertex that is just arranging all the pieces in first 2 rows and last 2 rows, and every move will move you from one state to the other. A vertex doesn't have to be just a single position of a single item or thing. There is some initial state in our grid problem. Let's say that box is at 5-2 and the player is at 6-2. From that we can move to several other states, maybe 0. But if it's a neighboring cell, then we can sometimes push, and that would be of cost 1, because we want to minimize that number of pushes. This is what is interesting for us. And then we will have some state. But also a player can move to a neighboring cell, maybe with cost 0. We don't count those as a move. With cost 0, we can move maybe to 5-2 and 7-2, maybe also to 5-2 and 6-3. This is other neighboring cell and some 4th possible move. I think that every time we'll have at most 4 moves, because a player can move in 4 directions. Maybe one of those moves will be a push to a box. That one will have cost 1. So here we have cost 1, cost 0, and I guess cost 0. And that's it. We have some big graph. The number of vertices in our graph is at most size of grid square, because, or we could also say that this is up to, say that this is height. Then h times this is up to w times the number of possibilities for this number is h times w, and this is the complexity. Then not complexity, this is the number of vertices in our graphs. Every vertex has at most 4 outgoing edges, so also this will be complexity for the number of edges. And if we can apply BFS, maybe Dijkstra will be necessary, but if we apply BFS, then this is the final complexity of our solution. Standard BFS has a starting cell and a queue where we just push new vertices. A has neighbors B, Z, F. Then we take the next vertex in this queue. B has new neighbors G and H. Then we consider Z that has a new neighbor J, and so on. Every time there are some vertices that are already in the queue, and we process vertices in the order of adding them to the queue. So now Z will add a new vertex J. Then F will add C, and this is it for this graph. BFS assumes that every edge has just cost 1. It turns out that it's also possible to give cost 0 to some vertices, but we should think about queue in slightly different way. Instead of just one queue, I will say that there is a vertex at distance 0 from the starting vertex A, and it's A. Then A has some neighbors, and those will be at distance 1 from the start, B, Z, F. Then B has some new neighbors, G and H, so I will put them at distance 2. There is G and H. Then Z will give me a new neighbor, so vertex at distance 2 from the start, this is J, and so on. And I will this way keep multiple queues, and every time when I'm at some vertex, at a queue of number 2, I will push to the next one, to queue number 3. The complexity doesn't change. The number of those queues will be at most O of n, the number of vertices, because this is limit for the distance from starting vertex to some new vertex. And we can, for example, think about it as an array of n queues. Still, every vertex will be considered by us at most once, just once, where we insert its neighbors to the next queue, and that's it. The complexity doesn't change. The advantage of this implementation of BFS is that it can handle lengths of edges that are different than 1. For example, 0 and 1. What is also possible is to have lengths bigger than 1, then complexity is increased. The complexity will be O of max distance. So this can grow very big if lengths of edges are up to 1 billion. But if lengths are up to, say, 5, this is still a better approach than Dijkstra. Here we have distances, here we have lengths 0 and 1, so this maximum distance will still be just n. But because we have also edges, the complexity is n plus m, number of vertices plus number of edges. How would our BFS work for lengths 0 and 1? We start with starting vertex A and consider all its neighbors, B, Z, and F. And every time when we have edge of length 1, we put that neighbor to the next queue, because we have distance 0, so that neighbor will have distance 1. I will put here B, then I also put here Z, but F has length 0 from me, so it has the same distance from the starting vertex. I will put F here when I consider this vertex. Then I will consider vertex F, just the next one in the same queue as I'm in right now. And from F I see a neighbor C. To that vertex I have length 1, so I will put it to the next queue, B, Z, C. Then I go one by one through vertices of the next queue, and so on. For B, I see neighbors G and H in the graph. So G has a new distance, 2 from the start, but H is at length 0 from me, so the same distance from the start. I will put it to the same queue. So for B, I had two neighbors, H and G, and one of them had length 0 from me, so it's the same distance from the start, and here distance 1 from me, so distance me plus 1 from the start. If from B to G there would be distance 5, then I would put it here at Q, that is my number plus 5. This graph doesn't have to be a tree, it can have some extra edges, so it's just any graph, and then we need to be careful if we want to multiple times insert the same vertex in one of Q's. So the thing, just like with other implementations of BFS or DFS, is to check if we are at distance x from the start and we have an edge of length L, then we need to compare if this is smaller than the current distance of my neighbor. If this is smaller, then it means that my neighbor is in this Q right now, Q of this number, but I want to insert it to this one. So I'm inserting to this one, and later when I consider this Q where it's also inserted, it would be a situation similar to the fact that maybe here we have H on the right, but also we would have H here in the second Q. When I consider H here for the first time, I go through its neighbors. I don't want to repeat that, so the next time when I see a vertex in some Q, I check if I already processed this vertex. If it's marked as processed, which means I already went through its neighbors, then I don't do it again, because that would increase the complexity. Assuming that for every vertex only once I consider its neighbors, the complexity is linear. Let's implement our algorithm. I already created a variable for height and width of a grid and a function available that will check if cell row and column it is inside the grid and not a wall. This will mean a cell that is available that I can move to. I need to find starting cell, also a starting cell of a box, and then run BFS with multiple Qs. Iterate cells of a grid, row call. If grid of row call is character B, then this is box. Start box will be row call. And if this cell is S, I think S is starting position of a player, then start me is row call, and it won't hurt me to already remember position of target. I will say if row call is T, then target is row call. Maybe this could be implemented with some for loop over 3 characters, but I want to have meaningful names, then this is fine. Maybe it isn't that bad at least. Start box, start me, and target. Each of those will be a pair of coordinates. To simplify my code a little bit, I will type uppercase P instead of pair of pair int int, pair of int int. Either this, and now I will say that starting position, vertex in our graph is start is make pair of start box and start me. This will be coordinates of a box and of player, that human in a grid. Either this, or maybe even better, is to create a struct for that. P like position, or let's just use position, where I have box and me. What I could use is this array of vectors of size max dist, where this is some limit for distance for the answer, and we could try to figure this out. Maybe it will be h times w, so size of the initial grid. Maybe it will be this times 2, because maybe we go back and forth. Some sure limit is h times w times h times w, because it is size of that new graph, where every vertex is pair of position of player and position of a box. Instead of that, I will just use a vector of vectors, and I will add a new Q if I need it. Well, I use a vector instead of Q because I'm not really going to remove elements. I don't need to. You don't need to do it in BFS. I find it easier to implement that with a vector. Initially, the first q or vector will just have the starting position, and then for distance up to q size, this will stop when we are out of this q. For every element of that vector of positions. So now I iterate vertices in a graph that are at this distance from the starting vertex. Q of dist.size. We have state q of dist of I. If processed, then continue. And processed should be a set or a hash set of positions. In order to make this work, I need to here create, unfortunately, a separate comparator. It doesn't really matter much, but it needs to be implemented in order to make this set work. Or if you want to use a hash set in C++, you need to here implement a hash operator, a hash function, so that some hash would be computed. In Python it's easier because it just works by default. A dictionary just works by default for tuples. Now iterate over for neighbors of my cell, because I can move there. I will say what new row, or let's call it new row, is state.me.first, which is my row, plus delta row of dir. New call is state me second plus delta call of dir. And what is this delta row and delta call? Something that is plus and minus 1, that it will tell me what, if I go in this direction, should I increase my row number or not? Should I decrease my column number or not? Delta row of 4 is -1, 1, 0, 0. Delta call of 4 is 0, 0, -1 and 1. For example, for dir equal to 1, what I would get is a pair -1, 0. This is a vector by which I will move, a math vector by which I will move. So from a cell 5, 5, I would move to 4, 5. This is one of my 4 neighbors. It's very convenient if you want to implement BFS or DFS in a grid. If I created a function for that available of new row and new call, then I consider moving to that state. New state of state.box, comma, a pair. Maybe I will just create 2 new things. New box position is state box. Possibly this will be pushed by 1. New me is just pair new row and new call. And if new me entered cell with a box, this means a push. And then new box first plus equal delta row of dir. We move it. If we moved like by 1 to the right, then we want to move by additional 1 to the right. New box second plus equal delta call of dir. And if not available, of new box first, new box second, maybe there is a wall there, or this is not a grid anymore, then continue. We computed new box position and new me position, so this is a new state, new position. If distance of new state is greater than distance of my previous state, which is state, plus length, L, then we do something. We say dist of new state update, and I will create a variable for these two. It's dist of state plus L. Here it is dist2. So dist2 is that distance to my current state plus length of edge. I need to figure out this length of edge in a moment. I will say that by default this is 0, but if this is a case, L++, if I'm pushing a box. This means I'm pushing a box. Yeah, and Q of dist2, pushback, new state. What is dist? I think that dist is a map from position to distance. And dist of that initial start is 0. What else do I need? Here I'm pushing to Q of number dist2. But maybe that one doesn't yet exist, so I will say maybe while dist2 is greater equal q.size, q pushback empty vector. Now by default I have a single q with one vertex in it. When I try to push something to q number 5, then I want that that q to exist. So I might want to add a new empty q. And by q I mean a vector, because this is how I implement this thing. And this happens before I push back. Otherwise I would get runtime error because this doesn't yet exist. This is a general way that works for any distances, any lengths of edges, not just 0 and 1. It's just that it would be slower if lengths were bigger. If lengths are really big, or weights of edges, then you should use Dijkstra. Here I wanted to avoid that extra logarithm factor, because I know lengths of edges are up to 1, so total distance is up to number of vertices in a graph. Everything will be linear. Maybe in some case I want to finish the whole program, and I will say here if state.box is equal target, so if box got to the target location, then I can just return distance. I don't need to save it in some way, because I know this is the first occurrence, and BFS considers vertices in increasing distance order, so I just return the current distance. If this for loop gets done, I return -1. Let's now resolve any compilation errors first and then logical errors. The semicolon after struct definition. I called this start box and start me, not box and me. Run code again. Line 67, dist of state. Oh, I reused a variable name. My map will be called map dist, because, or maybe better here, this is current distance, which is an int, and here I have a map distance. This current dist will just be here, here, and in return I can also say assert, just to make sure that my code is reasonable, distance of state should be current distance, just to check if I am updating everything correctly. And that reminds me of here, I compare two things, but by default, if new state doesn't exist, then this will be 0. So I will say if dist count new state is 0, or that. This checks if maybe new state doesn't exist in a map. Also would work for a set. My previous code wouldn't work. And we got wrong answer. Output -1, expected 3. What can I do? I can at least print which positions I do consider and I will here say maybe, oh, do I insert to processed, by the way? Processed. No, I do not. I should. Multiple mistakes. But this doesn't explain -1. It would, I think, just worsen the time. I will here say print state box first, state box second. This will allow me to understand if I consider more than one cell at all for this sample test. I'm confused now. Should I see anything printed, or maybe I didn't even once got to this part? Maybe. Okay, so I'm not. Maybe I should print with cout. A CRR B. CRR should be better because in some problems we print the answer and then CRR doesn't collide with that printed answer. Okay, cdout I see, but not cdr. Okay, then I should change CRR to cout. My bad, I don't know Leetcode that well. I'm considering cells positions 2, 3, 4, 4 and then 2, 3, 2, 3. Something is clearly wrong because instead of moving to a neighboring cell, I moved, it looks like a player moved immediately to a cell with box. It shouldn't be that way. What I'm pushing here, new state. What is new state? State box and new box. This obviously is incorrect. It should be new box, comma, new me. I'm happy that I got some mistakes, by the way. It's also a part of learning for you that you can see how I approach mistakes. I printed something, now I understood that, oh, that second line is clearly wrong, and possibly I don't create a new state correctly. Works for the first sample test. This doesn't mean that much, but let's submit. Maybe I will need to remove this cout because it might slow the program down. Time limit exceeded. Yeah, let's try that. It is possible that my debug, because it uses ENDL that flashes the output and is very slow, that it slowed the whole program down, that everything else is faster. And indeed, this is accepted. I got accepted, but not really with a great time. I'm faster than 5% of C++ submissions, and that's bad. But I think the complexity is enough. And I know how to solve this problem in a faster way that wouldn't create so many states. And that is to describe a state as position of a box and where a player is, right, up, left, or down from a box. Just to consider those states where we are just next to a box, and then from that either push a box or run a separate internal BFS to check if I can move from right from a box to up a box. But again, we have h times w states, and in each of them we run BFS, so the complexity is the same, is hw square, size of grid square, but maybe in practice faster because we don't create that many vertices. Memory will be better for sure. There is here some memory usage, less than 100% of C++ submissions. I doubt that this is correct, but you should focus usually on complexity. I said that many times, don't worry too much about those statistics in Leetcode. I think they reward squeezing your solution and using something slightly different, because then your time will be times 2 or like half of that. while it isn't really a better solution. That is safer, it's easier to implement, and it has better complexity. So don't worry too much about that. At least I don't do it, and in a real coding interview, your interviewer also will not care that much because you will likely implement something on a whiteboard. I hope you enjoyed this harder problem today, and feel free to give me some suggestions of other Leetcode problems to solve on this channel. Bye!